Good. So I promised you to describe the weak equivalences between the finite objects, between the infinity-operads. And the same description will actually describe, same formulation will describe the weak equivalences between infinity categories. Okay, so I'm going to say essentially surjective and fully faithful again. But I have to be a little bit more subtle. Okay, so fix an infinity-operad X. That's a dendroidal set. Okay? This is just a very simple combinatorial object. Now I want to think of it as some sort of operad. Okay, so it has colors. Its set of colors is X of this tree. Okay? Which is the same as hom from eta into X. Eta is the unit of the monoidal structure. Okay. Now, given such colors, C1, Cn, C, we can define an object X, C1, Cn, C. I say object, but I will be more specific in a minute. As follows. You can look at the corolla, Cn, and then hom it into X. Yeah? This is a dendroidal set. This is the internal hom. So that's the dendroidal set of n-ary operations of X. Okay. Now there are maps. Excuse me. There are maps. These are representable dendroidal sets. So at the level of trees, this is just a map like this, which sends this edge to one of these edges. Okay, there are maps for I equals 0 up to n. Just picking out the colors. Okay? So I get a map here to, by precomposition, hom okay, and this is the same as the product, of course, hom eta x, and that's the same as x to the n plus 1. Because eta is the unit for the monoidal structure. So this is, you have an n-ary operation and you evaluate it at the n entries and at the output. But we have our colors C1 up to Cn and C, and they define a map to eta, from eta. So this is C, C1, Cn. Question? So I take the pullback. So what is this object? Well, a priori it's a dendroidal set, right? It's a pullback in the category of dendroidal sets. Next, you observe as an object over eta. So in fact, it's a simplicial set. It coincides with its linear core, so to speak. So it's a simplicial set. But you can also prove, using this, among other things, using this tensor property that I ended with last week, but also a little more, which it would be a little bit too technical to go into now. You can prove that this is in fact a Kant complex. To prove it's an infinity category is sort of obvious from the model structure axioms. You have a vibration. You see this map from the coproduct of the etas to Cn is a cofibration, X is vibrant, and then you home, you get a vibration, you pull back a vibration, you get another vibration, so it will be an infinity category. But in fact, it's an infinity groupoid. Well, that's the intuition. Kant complex. So these Kant complexes all together form some sort of operad up to homotopy, yeah? In some vague sense, which I will not make precise. Not yet. So this is one thing we can do. In addition to this, if you have very simple construction, so fix an infinity-operad X, so we have these home spaces. We also have an ordinary operad in sets tau of X, and hence a category J upper star of tau of X, which is the same as tau of I upper star of X in this case. Okay, I'm running around the square. Let me write the square again. Simplicial sets, dendroidal sets, operads, categories, J upper star, I upper star, tau, tau. Okay? Now be careful, because these are right equivalent functors and these are left equivalent functors. So this square does not normally commute, but it commutes on vibrant objects. So this equation is not a tautology, okay? Because X is an infinity operad. Okay. And then we have the following proposition, or maybe part D of the theorem, I think. I forget, it's still here. So part D of the theorem. A map y to x between vibrant objects i.e. infinity operads is a weak equivalence if and only if it is fully faithful, x c1 cn c to y fc1 fcn fc is a homotopy equivalence of Kant complexes for all colors, i.e. ci in x of this tree, and where is my category? Tau I upper star of x to tau I upper star of y is an equivalence of categories. As a corollary of this, but this was proved earlier by Joyal, and there's also a version by Lurie, you get exactly the same statement for infinity categories. Okay, so the same is true. I will not. And that's actually a consequence because it's also.
The map f should go from x to y, no? Or the
Yes, thank you. I'm not very. Thank you. So there is again a considerable overlap in these two conditions. Yeah? This is fully faithful. If you calculate the arrows in this category, tau I upper star x between two objects C and C prime, that's actually pi 0 of x C C prime. This is a chem complex. This is a set of connected components. Okay. So to say that this is fully faithful is already contained here, but to say that it's essentially surjective is not. Okay, so now let's move to simplicial operads. I say simplicial operads, but if you prefer, you can work with topological operads. But do remember, they're colored. The colors form a set. Colors don't have a topology, and the maps can change the colors. Okay. So I will we denote this category. Denote this category by S operads. So there is a particular operad which I will also call eta maybe. Write eta also for the unit operad, one color, an identity operation only. It's like the 1-point category. Okay, so then you have a similar thing as for dendroidal sets, namely simplicial operads over eta is simplicial categories. Categories enriched in simplicial sets. Question?
Yeah, you can do simplicial operads, topological operads, but can you do operads over DG operads, for instance?
Sure.
Okay.
But I will not model them by dendroidal sets.
Yeah.
Okay, I will get back to that.
Okay.
Good. So how can we go from dendroidal sets to simplicial operads? This functor tau, as I mentioned, well, it's still here. This functor tau on the set of operations, it only sees the connected components. So it throws away all the higher homotopy. So that's not very good. How can we go from dendroidal sets to simplicial operads? By retaining this information. And now I'm very glad that Bruno asked me to talk about Boardman-Vogt in the introductory workshop, because I will use it. Sorry?
He's congratulating himself.
No. Math is copy.
Okay. So consider the functor W, small w, from omega to simplicial operads, sending a tree t to w of t, which is, we have an operad omega of t, and we take its Boardman-Vogt resolution. Is Boardman-Vogt resolution of T as opera. So the colors of, just to remind you a little bit of the flavor, the colors of W of T are the edges. The operations of omega T are generated by the vertices. So there is an operation from AB to C, and there is an operation from CDE to F. And in the Boardman-Vogt resolution, I'm going to put a length on the edge C. So there is a delta 1 or a 0, 1 space of operations from A, B, D, E to F. Okay? That gives the simplicial enrichment. Okay. And now you can, of course, take the can extension of this functor. So this induces an adjoint pair where are we? Let me write it here. Dendroidal sets, simplicial operads, W shriek, W upper stop. Okay. Of course, I could do exactly the same for delta. Yeah, delta is contained in omega. I could take the Boardman-Vogt resolution of a simplex viewed as an operad. Simplex viewed as an operad is a category. So you get the Boardman-Vogt resolution of a category. It's a simplicial category. So there is a commutative diagram, maybe doing exactly the same. For delta, gives a commutative square so I'm hoping I'm getting this right. Let me write this again. Excuse me. So these are the left adjoints, and everybody has a right adjoint here. Okay. And this lower part is maybe something, an adjoint pair that you know, because W upper star over simplicial category C is exactly the homotopy coherent nerve of the simplicial category. Yeah. So when I said 3 weeks ago that Boltzmann-Fock resolution defines homotopic coherent nerve, which was something, of course, known to Vogt, this is what I had in mind. Yeah? Okay, and you get the lower row just by slicing the upper row by eta. The lower row is obtained, can also be obtained. The lower row with all its properties, which I haven't quite stated yet, obtained by slicing over eta. Okay, so the main theorem, well, maybe I should say something else first. So proposition, there is a model structure of simplicial operads where P to Q is a weak equivalence if and only if. And I'm going to write almost the same as I did 5 minutes ago. P, let me give the map a name, F. P C1 Cn C to Q F C1 F Cn Fc is a weak equivalence of simplicial sets for all colors C1 C. So now you should protest a little bit, because what do I mean? I mean here classical Kant-Quillen, okay? Because well, I suggested this already when I said you may choose whether you want to talk about simplicial operads or topological operads. Yeah. And the other condition is that if you take J upper star of P and you view it as a category, am I doing this correctly? What is this? Okay, sorry. If I restrict to the unary operations, I get categories enriched in simplicial sets. Now I take pi 0 of all the Helm sets. I get an ordinary category in sets. Okay, so I take pi 0. Pi 0 is an equivalence of ordinary categories. So if this there's one where okay, we could stop the sentence here, maybe. So these weak equivalences, if you restrict yourself to unary operations only and you talk about simplicial categories, you get a model structure by slicing over eta. And the weak equivalences there are known as the Dwyer-Kann weak equivalences of simplicial categories. And this is a model structure due to Julie Berkner. So by slicing over eta, we recover the Berkner structure on simplicial categories. So the fibrant objects are quite simple to describe. They're just the simplicial operads, all whose spaces of operations are Kant complexes. The cofibrant objects are not so easy to describe. They have a lot of freeness in them. So there are not many cofibrant objects. And it's completely different. I think if I'm about to compare this to dendroidal sets, and maybe this is the most striking difference. For operads, you really have to make everything free to get anywhere near cofibrant. For dendroidal sets, you just have to make the group actions free. So it's much easier to be cofibrant. And this is also the reason underlying the fact that the tensor product, about which I haven't talked at all today, is very well behaved on dendroidal sets. It's a monoidal model category, but on operads it's a total mess, because if you take the product of two operads, you get commuting squares, and it's far from free. In other words, the tensor product of two cofibrant objects doesn't have to be cofibrant. Okay, so let me now state the theorem that I wanted to state earlier. The pair dendroidal sets W shriek, W upper star, simplicial operads is a Quillen equivalence. So if you see a simplicial operad, you can take its homotopic coherent nerve and move into some sort of combinatorial world. And if you see an infinity operad, an operad up to homotopy in some sense, you can strictify it by moving to simplicial operads. It's no longer up to homotopy, but it has more simplicial dimension in it. So, as a consequence, so by slicing over eta, it's still there. Simplicial sets to simplicial categories is a Quillen equivalence which was known, but I should have prepared the history a bit, but you have to combine a few results of Joyal Tierney, and Lurie, and maybe Julie Bergner. Because the way this is being proved, but I don't think I should go into this now. You're probably getting a little bit tired already, but you put lots of, one doesn't prove directly this is a Quillen equivalence, but one constructs a zigzag of Quillen equivalences, which turns out to be homotopy equivalent to this one. So there are lots of other Quillen equivalent models sitting in between. And maybe one thing, a special thing that I would like to mention is if you don't like colored operads, for those who still don't like colored operads, you can do the following. There is an induced Quillen equivalence where you take simplicial operads, no colors, or just one color, on one color, with the model structure which that I gave as an example in the very beginning. Yeah? You just have the PNs. And then on the dendroidal set side, you can do something which is familiar to many of you in the context of simplicial sets. You just talk about reduced dendroidal sets. They have just one vertex. Where RD sets is the category of reduced dendroidal sets. I.e. those X for which x of this is just a one-point set. Okay, it's a full subcategory of dendroidal sets, and you can put the same weak equivalences and the same vibrant objects and play around a bit so that the model structure here induces one there, and you can relate that to classical model structure here. So maybe I will state the theorem without giving the precise definitions, and then we will have to see what we do about this in the coming weeks. So recall that there is a model structure also on simplicial sets plus over the nerve of gamma op with vibrant objects are Lurie infinity-operads. Well, I'm going to say a few words about this. Don't worry. Okay. So simplicial sets, you know. Simplicial sets plus is the category of marked simplicial sets. Okay, they are pairs, a simplicial set and a set of one simplices. Pairs X and M containing X1. And they should satisfy some conditions. For example, all the degenerate one simplices should be marked. Yeah? And gamma is Graham-Siegel's gamma. So gamma op I like to think of as the category of finite sets and partial maps. Which is the same as finite pointed sets and pointed maps. Because if you throw away the base point, then the map becomes partially defined only. Okay? Now, so among these partial maps.
Sorry, what do you mean by partial map?
A map which is only defined on a subset.
Okay.
So there are some special partial maps. Special partial. So any injection B, I hope I'm getting this right, and A defines a partial map A M inverse B. Okay? It's an isomorphism on its domain. And these are called inert. So these are arrows in gamma op. So there are one simplices in its nerve, and you can mark them. Yeah? You can mark them. So nerve gamma op neutral is the nerve with inerts marked. So I don't have time to define this, but for those who know, or just to advertise, let me do it like this. So theorem which I proved with Heuts, was a student of mine in Utrecht, and he's now at Harvard, and Hinich, who will come here in a few weeks.
A few days, if you can come.
Yes, I know what you're referring to, but let's not. Okay, so there is a Quillen equivalence, there is a zigzag. What Quillen equivalence is between dendroidal sets and simplicial sets plus of a nerve. So, now I have to think a little bit. I think the shortest zigzag goes like this. Let me know. I mean, I can figure out by writing a few more things on the board, but that's not very bad at me. So another model for these operads of the homotopy is the one by Lurie, but it's in fact equivalent to dendroidal sets. So maybe as a closing remark, so I said that, where is it? Yes, these three equivalences are proved in a rather indirect way. Okay, so let's call this theorem 1 and theorem 1 and 2. So theorem 1 is proved in an indirect way via a model structure on simplicial sets to the omega op, which is dendroidal spaces. Okay, so on dendroidal spaces, maybe I will just say it in words, and if you're interested, you will have to look at the papers that I wrote with Trzynski, or ask me some other time. So omega is a little like a Reedy category. So you can put a Reedy model structure on this category, and then you can put a Siegel condition which forces the existence of operatic compositions up to homotopy. Yeah? So just to give you an example, if you, maybe I can be more precise. The vibrant objects have to satisfy a Siegel condition x of t to x of lambda et is a weak equivalence for any inner edge E in a tree T. Okay? X is a functor from trees to spaces. So this is a space. This is a union of trees. It's a union of faces. So if I write X of such a dendroidal set, I mean the limit as usual. And you can ask this to be weak equivalence. Okay. The 3D structure, in fact, forces this to be a vibration, so it's a trivial vibration and it's much easier to handle. And this category of dendroidal spaces with this model structure is also equivalent to dendroidal sets and to simplicial operads. So if you want to put in some additivity, some algebraic structure, and you want to go to algebraic operads, I suppose what you have to do is to look at dendroidal chain complexes, put again the 3D model structure, localize it for a single condition, and that should be equivalent, but I haven't worked it out, to DG colored operads. So I will close with this somewhat speculative line. Thank you.
Can you say one word about, you said that these two categories, your dendroidal sets and your marked simplicials, they both model operas in infinity-operads. What is the advantage of why should we work with this one, why should we work with the other one?
I think you should work with dendroidal sets.
Okay. That part of this.
No, but more seriously.
Yes.
So the advantage of Lurie is that you can. The advantage of Lurie is that it's very fast. The advantage of the Lurie category is that you can use the standard techniques of simplicial sets if you train yourself in carrying the markings along. The advantage of dendroidal sets is that it is, in some sense, a much smaller model. It's a small combinatorial model, but to learn to work with it, you have to develop some experience because it's like simplicial sets, but it's not quite. But objectively, the main advantage of dendroidal sets is it's a monoidal model category, and Lurie's is not. So, for example, to model EN operad, you take S associative operad, it's even discrete. You take its nerve, a homotopy coherent nerve, but it's the same as the nerve. You get a cofibrant object here. You take tensor powers to the n. You apply the W shriek, and you get En. Yeah? So something like this is also true for Lurie, but he has to sort of fake this tensor product because he doesn't have a good tensor product. He has a construction on fibrant objects, which is not symmetric, and so it's symmetric up to homotopy. So I think the fact that this is monoidal is the main objective advantage.
So is the clone equivalence monoidal? Is it monoidal?
That's a good question. Which one?
Between dendroidal sets and Lurie's or is there some at least comparison?
Yes. So they're all monoidal. So there is a weak W. Well, this W shriek, if you apply it to the tensor product of cofibrant objects, you get something equivalent to the Born-Mafog tensor product of the W shrieks. And for Lurie, something like this is also true for the. Where is Lurie? I wrote the zigzag, did I?
Up there. Up there, on the right.
Sorry, that's it.
On the right.
A zigzag. Ah, here. Yeah. So the easiest functor is to go a little bit in this direction. I can tell you a bit about this proof, but then that functor is also easy to control on tensor products. So there is a bit of a zigzag in here, but it is sufficiently monoidal. So I can tell you a little bit what you do. These are trees. Okay. Now in the nerve over gamma, you have gamma log. You have sequences of finite sets. Okay. So here you have 3 elements, and here you have 2, and these map to this one, This maps to this one, and then this maps just to this one, and this here, the next map is undefined. You get things like this. So you get things which looks like forests with levels. There can also be things which start here, which I will write like this. So from Lurie you can construct what are some sort of marked forests. Yeah? So what we have to do is introduce, I'm trying to point to my zigzag, introduce markings here. We replace trees by forests. And then we are able to sort of relate the two. It's still not by quite equivalent pair. Yeah, there's another very strange thing, namely, in Lurie you have the empty set. It's a finite set, but it's a representable, so it is there. So if you have an object for Lurie, it has a fiber over 0, which is a big simplicial set, which is being carried along all the time. Yeah? But for finite objects, this is just one point. It doesn't play any homotopy role. So this is something you also have to get rid of to construct this equivalent. So these are some of the ingredients. Okay. Other questions?
No.